Thank you very much for the invitation. So I will continue explaining how the conformal block appear in this picture and in the conformal bootstrap using this what Remy explained on this the spectral resolution. Okay, so the Hilbert space Remy defined it. It was L2 of H minus epsilon. Okay, I will use S1 for the circle because I'm just more used. I think he used some measure on you. This can also be viewed as L2 on the real line with the parameter C. C was this zero mod in Remy's talk. Time okay, omega S1, which is like a set of sequences. So these were these Xn and Yn, the probabilistic space, and the measure was dc dp. dp was the product of it was the product of Gaussian measure for n bigger than 1. This is the Hilbert space of the, so it's a separable Hilbert space. We have found two kinds of bases. One was given by the free field and the other one by the Virasoro. Because there is this Laplacian in the real line, the basis involved a sort of Fourier transform, so there is a continuous parameter P. Now I want to define what I call Liouville amplitude. Okay, so to define a Liouville amplitude, we need to start with a surface sigma, in general with boundary. Not a compact surface with boundary. I think we need a metric G. And then something that I will denote Xi, which will be a boundary parameterization. So I'll make a picture here. I'll just take, for instance, a pair of points. 1 of sigma, 2 of sigma. This I have 3 boundary components. And I have Xi is Xi1, Xi2, Xi3, where Xij is an analytic map, real analytic map from S1 to the boundary. The J's boundary component is going to be real analytic. So it's an embedding of the circle, of the unit circle. So this will be C3, for instance. An embedding of the circle S1 into the boundary. So why we need this parameterization? The Hilbert space is defined on the circle. It's just a set of random field on the circle with some distributed with some Gaussian measure, and the circle for us is just a canonical circle. Now we want to embed this circle into the boundaries. As Remy explained, the idea will be that we will cut surfaces. We will cut the path integral in pieces by conditioning on some set of circles. So for instance, on a genus 2 surface, we could cut here, here, and here. We get 2 pair of points where these are glued, these are glued, these are glued. In general, any surface can be cut in such a way. And when we have marked points, we can cut also in terms of this marked point, and there will be some building block if you want to do the conformal bootstrap. The surface will be decomposed into pair of points when they don't have marked point, and when you have marked point, the two other building block of the decomposition would be an annulus with 1 marked point or a disk with 2 marked points. So each surface with mark point can be decomposed, not in a unique way, but you have to fix some topological cutting curve somehow. But they can always be decomposed into, if it's genus G, it will be 2G minus 2 plus the number of mark point building block, which is either a point, an annulus with 1 mark point, or a disk with 2 mark point. And an annulus with 1 mark point, you can also view it as a point. When you shrink, you pinch this curve to make a mark point. It becomes an annulus with 1 mark point. And if you pinch now these two guys, you get actually a disk with 2 mark points. So this mark point can be viewed as a kind of limiting case of when you don't have mark point. It's a bit like going to the boundary of moduli space. Okay, so we have this parameterized boundary. What is the Liouville amplitude? I will define it now. So A sigma G. So G, it will be a metric with a geodesic boundary also. So the geodesic curvature is 0 you choose the metric G like this. So when you have G induces J, which is a complex structure. And sigma. Okay. For each complex structure, you can take a compatible metric, but if you have a metric, it induces a complex structure. But somehow, in the Liouville theory, we need to use a metric. We cannot work directly with complex structure because it's a theory of random metric. And in general, for CFT, it's quite convenient to use a choice of metric in the which is compatible with a complex structure. So the Liouville amplitude A associated to this surface with this Riemannian surface with parameterized boundary is going to be an element in L2 of H minus epsilon of S1 to the power 3. Sorry, to the power B in general. If you have B, so let's say you have B boundary component, here it's 3, but I could take even more boundary component. And the measure is just the product measure of mu to. So it's going to be an element in this Hilbert space tensor 3. Okay. So for each surface, we will associate this. Sorry? Sorry. Oops. All right. So in my example, B was 3, but in general is B. And I want to, okay, there are several ways to view it. Either it's you view it as an element in the Hilbert space, but you can also view it as an operator, okay, as a Hilbert-Schmidt operator, by thinking of it as an integral kernel. Like Remy explained for the annulus, there was this propagator and there was this sort of integral kernel of the operator. So what is A sigma? So I will have to take 3 fields, sorry, B field in general. So remember phi in the talk of Remy, phi j was a random field whose distribution law was given by this mu measure, this mu here. So it's just given under the same, it's the same formula, root of n and theta. 1. Then you have the same thing, the conjugate part of the negative Fourier mode. It's a real valued field here, phi j. And then you have a C, which is the 0 mode. 0 Fourier. So each field will be something like this. So of course, I should put a J maybe here, because each one has different components. Like this. So now the definition is similar to what Remy said. So for it's something of the same kind at least. It's going to be a free field amplitude so this whole thing I will call it phi also. This whole collection of field. A of L0 of phi times some. So this is the free field one, the free field amplitude. It's a bit like for the propagator or the semigroup of Virasoro that Riemann defined. You had the one of the free field, and then you had the potential. And the potential term is given as follows. So it's a conditional expectation on phi of a potential term, which is the integral on sigma of Q was this parameter of the Liouville theory. It was gamma over 2 plus 2 over gamma. Gamma is a parameter between 0 and 2. Here you have the scalar curvature of G. Time x plus p phi. So x is the Dirichlet GFF, Dirichlet Gaussian free field on sigma. So it's a random field with value in distribution with covariance given by the Dirichlet green function on sigma. P phi is the harmonic extension on the surface. And then you get the Gaussian multiplicative chaos measure here. The d volt. So this is the Riemannian volume measure. So it's here I view it as it's really like the integral kernel of an operator. So it's a function of the field. If I want to define an operator, from this I can define an operator. So for instance, if B is 3, I have a pair of points. The idea is we want to view the amplitude here as an operator mapping from H to, for instance, the tensor product of H. So H will be attached to this boundary component, and the two other one will be here and here. So it's a bit like a propagator from one boundary to the two others. And how you will define it? So this A. So I keep the same notation here for A. A of F of phi sigma G xi. So this is now an operator. I view it as an operator. I can define it as the integral over h minus epsilon of S1 of this integral kernel A sigma G xi of phi1, phi2, phi3. So here, sorry, it should be phi1, phi2. So let's say this is D1 sigma, D2 sigma, D3 sigma of f of phi3, for instance, d mu phi3. So if I take my integral kernel and I view it as an operator going from this entry to the two others, I get really an operator here from H to H tensor 2, and so on. So I can also view it. So this is one way, but I could also view it as an operator going from H to the tensor 3 to C to C, for instance. Just because it's an element H to the power tensor 3, so I just make a scalar product. And so there are many choices possible, and in fact, these choices are related also. Practically, they're related on the orientation you choose on sigma j. Sigma j, this parameterization can be either positively oriented in the surface or negatively. And the convention is that if we orient it positively, let's see, this one is positive and the other one negative, then we view the operator as an operator from the positive to the negative or incoming to outgoing. You can play with this and then you can revert orientation and you get many different operators. But in the end, it's more or less the same. So we have this Liouville amplitude.
Right, if you change your parameterization, does this change in the sort of obvious way?
No, it's not obvious.
Okay.
Actually, that's a good question. It's a bit complicated. Of course, if you do an easy change of parameterization, like just rotation, then that's not too bad. But, so this is why it's very important. The parameterization is very important. So you really get, it's really a function over the space of parameterized Riemann surface, which is like a universal rotational space. Yes, because you really choose the parameterization. Okay, so now we have this amplitude. How to relate to the correlation function and to what Rémi explained. Okay, let me give an example, and this example will more or less explain everything. How to compute the partition function of a closed surface of genus 2. So what I do, I will cut it in a certain way. Of course, the choice is not unique. That's not what I wanted, actually. I will take another choice. So in my picture, I want to have it in this. So I view sigma as I split it into two pieces. So let's say this is the curve C1, this is the curve C2, and this is the curve C3. I view sigma as the gluing of sigma 1 and sigma 2. So of course, sigma j, I choose a metric here on sigma. So the metric induces a metric on each sigma j. So I get sigma j gj, and then I have I choose also a parameterization of the embedded curve in the surface, an analytic parameterization, and I call it xj, the parameterized surface. Now, what is the partition function? I will call it A sigma G. So of course, sigma is the closed surface. I can also define the amplitude of a closed surface. Of course, in this case, I don't have the conditional expectation, and this is the way the Liouville partition function and correlation were defined. They are defined in terms of expectation of certain functional of the Gaussian free field on the closed surface. And now, this thing, which is really an element in R, no? What we can show is that you can decompose it as a triple integral of the two Liouville amplitude of the surface with boundary. So you get sigma 1, G1, C1 of Phi1, Phi2, Phi3 times A of sigma 2, G2, C2 of Phi1, Phi2, Phi3. Then we get d mu 1 P1 mu 15. And the idea, okay, this needs some proof. I mean, it's not really obvious, but the idea is really that here, this A sigma, which was given by some expectation of exponential minus 1 for integral of kg q x plus mu exponential gamma x dt. Something like this. Maybe there is some determinant of Laplacian also. And x is the GFF, I put it x of sigma. X sigma is the GFF on sigma. And then there is also an integral over c. Oh, I forgot. So it's x plus c. So the GFF on sigma is orthogonal to constant, so I have to separate it somehow. DC. So this is the way this partition function of the closed surface is defined. It's some expectation of some function of Riemann field. Then you have the zero mod. It turns out that if you disintegrate this expectation by conditioning the value of the GFF on this circle using Markov properties of the GFF, one can prove that they decompose under a product of an integral into of these two amplitudes. And in terms of Hilbert space, that's quite nice because you really see that you get a scalar product of two elements. In the Hilbert space tensor 3. So this is nothing than a scalar product. And now the idea of the bootstrap and why the conformal block are coming is that we will decompose this scalar product using the basis that Remy explained. And this basis has a special feature. So we want to decompose this using the spectral resolution. So I use the spectral resolution now. It was explained in Remy's talk. For these things. So of course, well, I mean, here there are 3 copies of H, so I need to use 3 times the spectral resolution. So what you get that A of sigma G is just the integral over R plus to the power 3 time, so you get the sum over Young diagrams mu1, mu2, mu3. So T for me we denote the set of Young diagram. Then we get the sum of mu tilde. There were 2 copies of Young diagrams in the spectral resolution. Okay, I will assume that the element in the spectral resolution. So let me explain that there was this function that denoted that Q plus IP nu tilde, and spectral resolution. The basis was given by P in R plus, nu in the set of Young diagram, and nu tilde in the set of Young diagram. He explained that these guys are not diagonalized and you need some Gram-Schmidt coefficient. I will assume that the Gram-Schmidt coefficient is 1 to simplify, but one should keep in mind that they're not really orthogonal. So if they were really orthogonal, what you would get is the following thing. So you get this time A sigma 1, G1, C1, and scalar product with CQ plus IPJ nu J nu tilde J in the Hilbert space to the power 3. And then, so this is the first guy, and then time, the other guy is product of IPJ nu J nu tilde J A sigma 2 G2. And then you get dp1, dp2, p3. So this is the decomposition using the spectral resolution. So now, okay, and then there is this Gram-Schmidt coefficient that I forget. So in fact, here there should be some Gram-Schmidt coefficient. And well, actually, in this case, we should sum over more young diagrams. So let me forget the Gram-Schmidt. So now the main thing is, can we compute this matrix coefficient of this amplitude? Is it possible to compute them? And this is actually what is called the Ward identity. This is where the conformal block comes from in this bootstrap result. So what is the Ward identity? The Ward identity is basically the context version of the symmetry of the model. So what do I mean? If you take, let's say I take a surface with boundary, like my pair of points, and I view it embedded in a bigger surface. Yes. So this is my, let's say my sigma, for instance, this piece. What there's a very nice property of this Liouville amplitude that I define is that if I take f, let's call sigma hat the closed surface, the one where you have glued, for instance, this 3 disk. If I take a biholomorphism, which map, let's say, sigma to f of sigma, and let's say f is close to identity. So I move a little bit my sigma by a biholomorphism. And one way to do this is to use the flow of vector field. You take a holomorphic vector field on your surface. Okay, maybe it's not possible. Then you could always put some poles here. For example, a meromorphic vector field. The flow of this meromorphic vector field for small time will just move a little bit your surface, your surface with boundary inside the closed surface. And there will be biholomorphism, because the flow is going to be a biholomorphism if your vector field is holomorphic. So now, if you take such an f which is close to the identity, it turns out that if you compute the amplitude of f of sigma, so let's put g hat, a compatible metric on the closed surface, which restricts, of course, to sigma and to f of sigma. You can actually compare. F compose. So you have your parametrization, like C1, C2, C3. You can compose on the left by this biholomorphism. It gives another parametrization. If you do this, it turns out that you get the same value for the amplitude. C. So here, what I mean is really F composed with C1, F composed with C3. But not quite. In fact, what you get an additional term, but which is completely explicit and which involves the central charge of Liouville, which was 1 plus 6u squared. It's called the conformal anomaly. So I'll denote it S of omega. And what is omega? Is what you get if you push forward G hat and you compare it to G hat. Because F is a biholomorphism, it's going to be a conformal map. So it will push the G hat metric, which is defined on the closed surface, to a perturbation, and you get a conformal factor here. So omega is a function, at least near, just smooth near sigma. And this is completely explicit. It does not depend. So remember, A was a function of 3 fields. In this case. but this C here just depends on omega and not, maybe it depends on G also, on G hat, but not on this phi. So it's a deterministic coefficient. So this thing basically tells you that this Liouville amplitude, they are essentially conformally invariant. So now, if you quantize this relation, this will give you some identity on the field theory. And this is the word identity. So let me explain what this is now. So the word identity, the first way I want to write it is as follows. So sigma 1 G hat C1. I want to take the product with this spectral resolution. Just to check, at what time should I start?
It started like still go like 20 minutes, 25 minutes.
So I still have 20?
Yes, 20.
So the one identity tell you that if you look at this, the matrix coefficient of this point amplitude, which appear here, it's actually given by the value of the amplitude on the ground state So this was the ground state in Rémy's talk. Here, by empty, I mean there is no Young diagram. Time, some coefficient, so I denoted by W, nu1, nu2, nu3 of P. So P would be P1, P2, P3. Oh, sorry, P is P1. These are these momentum, these Fourier coefficients of the spectrum coefficient Pj. I put them in a single element. Time W bar of W1, W2, I think that's yes. So you see the matrix coefficient of the descendant state, the one where you apply this Virasoro element, they are given by the matrix coefficient on the ground state times some coefficient, and it's split into two parts. I call them W and W bar, and this one are for the nu tilde, for the L and tilde. So there is a kind of separation. It's like a tensor product somehow. And this W, they are purely algebraic. It basically depends on the commutation relation of Virasoro algebra. I will explain you the link with what I said also with F here. So W, nu1, nu2, nu3 of P are algebraic coefficient. What I mean by algebraic is really depends mainly on Virasoro commutation relation. And what is nice is that if you remember this CQ plus IP empty set, is an analytic continuation of what Rémy called C alpha. So analytic from when alpha goes to Q plus IP from the real line to this imaginary line. We explain that there is a probabilistic region where this psi alpha state which actually is not in the Hilbert space, it's in a bigger space, but anyway, it has a probabilistic representation. And this P alpha of phi was given by some conditional expectation of some Gaussian multiplicative chaos on the unit disk. So I think it was alpha q motion. Maybe there's q minus alpha c here. It was given by a conditional expectation for alpha real.
The exponent of x is alpha gamma.
Alpha gamma.
And there is a minus in front of the q minus alpha c. And another minus in front of q minus alpha c. Yes. Yes.
So this was the expression for this graph. So now the nice thing is that if you come back to here, this is a conditional expectation. This guy is not really quite a conditional expectation because here you're at q plus ip, but this is the analytic continuation of a conditional expectation. So you can analytically continue this, you come back to alpha, and you get a product which is completely in terms of some expectation. And if you compute it, you find that this is the 3-point correlation function. This is exactly the expression of the 3-point correlation function on the sphere with weight alpha 1, alpha 2, alpha 3, with 3 mark points. And you can interpret it as a gluing of this amplitude, which is this sigma 1, with 3 disks with some mark point. And this one has weight alpha 1, this one alpha 2, and this one alpha 3. So the result is that this thing the tensor product of C alpha j empty set j equal 1 to 3 h is tensor 3. It is actually the 3-point function. So this is what is called the DOZZ factor. And in fact, there is also a constant depending only on the metric. This is a metric constant, which is explicit. And this thing is the 3-point function on the sphere. Okay. And this is true for alpha real, but this analytic continue because this formula, the DOZZ formula, is completely explicit. It's a special function which actually analytic continue. So what we see is that here, the matrix coefficient is given by the DOZZ function, the 3-point function, times some algebraic coefficient. So now if you combine everything, you come back to here, you get a DOZZ factor here, a 3-point function, here a 3-point function, and time a product and sum of a completely algebraic coefficient. And this is the bootstrap. So the final formula, if you combine this thing with this expression here, give you the bootstrap formula. It tells you that the partition function z sigma g, which I denoted also by a, is actually the integral on r plus to the power 3 of the DOZZ factor q plus ip1, q plus ip2, q plus ip3. Here you get the same thing, but with a minus, because for the scalar product, it's a bar. And when you take the bar of those, it's like taking q minus. Time some coefficient fp to the square, dp1, dp2, dp3, And this FP is what is called the conformal block. And this FP is just a product and sum of this W coefficient here, which appear in white. You just have to recombine if you want this integral by using this formula, taking into account that here this guy is nothing more than the DOZ. Which means the 3-point function on the sphere with the canonical metric or with a certain particular metric. This is the bootstrap for genus 2 surface, but you see that all this picture, because we have decomposed into pair of points and the word is for one pair of points, it actually works for any surface. Then it becomes a bit combinatorial. So now there is a particular feature of this conformal block. The conformal block, of course, here I did it for one fixed closed surface. But the nice thing about this conformal block is that if you think of it as a function on the complex structure of the surface, it's going to be holomorphic.
Just clarify one thing. So what you call the word identity is just this identity on this top board in the left?
Yes.
This is the fact that the inner product with some of your amplitude with some descendants is given by
the amplitude on the primary field times some algebraic coefficient.
This is word identity.
Yes.
Let me check. How is this related? I missed this other part of this. Is this like part of the proof or?
Sorry, related to this? Or?
Oh, yeah, this
equation. I will explain a bit this idea because here, of course, I told you this is given by this.
Okay, I can take this.
But this factorization somehow, or at least the fact that these are algebraic coefficients, come from this idea. The fact that the amplitude is not moving. Okay. And we will use the flow of deformation that Remy explained to prove this. And the idea will be to take a meromorphic vector field with a pole here, only here. We take a vector field, a meromorphic vector field with a pole here. We take its flow for small time. It will move a little bit of my surface into this bigger Riemann surface. And we will differentiate. So here we will get a T if you want. Ft will be the flow of a vector field, of a holomorphic vector field, meromorphic vector field, but whose pole is outside sigma. We will differentiate this identity. So here there will be a T maybe. And you see that this guy is not depending on T. So the differentiation here is just 0. Maybe you get a deterministic term, which is not troublesome. And it will give you some relation here.
Yeah.
And this relation, if you evaluate it on this descendant state, the fact that the meromorphic vector field, when you look at this will be related to the propagator that Remy explained. You will see the Ln coming, the Virasoro generator. And these guys are constructed out of this Virasoro. So this is the idea. Why? Okay. So I'll try to explain a bit more. So what are the blocks? The block I define them like this using this W coefficient. There is a subtlety here, is that a priori, the block could depend on the parametrization I chose to cut the surface. Because these amplitudes do depend on this choice here. I could take another family of curves, for my surface. I chose a certain family of parameterized curves, but I could, even with the same topology, I could take another family which is closed, like those one, and there would be like those one. So I can try to see what's going on when I deform the curve where I cut. And a priori, it's not clear that this block is not moving. And it turns out that it's actually moving. So the block is not going to be completely intrinsic function. It's really something depending on the cutting curve. But the way it depends on the cutting curve is not so troublesome. It's going to be by some deterministic anomaly, which involves some Schwarzian derivative of this parametrization map. Okay, so let me explain a little bit this. So I want to define now, okay, so just one theorem maybe, is that as a function of the complex structure, if I look at the block, a priori the block depends on the Riemann surface. This is a closed Riemann surface. J is a complex structure. So this guy is in C. It turns out that this is a holomorphic function on the Teichmüller space. The Teichmüller space is the space of complex structure up to gauge, and then this is a holomorphic. This is a complex manifold of finite dimension. So the block is going to be actually a holomorphic function. So this is a consequence of our construction. So now, how to really understand more the block and this W coefficient? For this, I need the block amplitude. I want to define something which is related to this Liouville amplitude, but I will call the block amplitude of, let's say, for instance, sigma 1, G1, C1, which is this pair of points. What is the block amplitude? It's going to be a function B, depending on P1, P2, P3, which are this momentum parameter. And it's going to be a function on a triplet of Young diagram. And this is nothing more than the Fourier coefficient with respect to our basis of the amplitude, the Liouville amplitude of the pair of points. But this guy depends on the metric. So what I will do this, and I divide by the same thing but I put the primary field here. Okay, so I take the matrix coefficient, but I divide by the 1 if I take the primary field. So in particular, for nu j is 0, this is just 1. And here it's very important that I just take the, on the nu tilde component, I put nothing. So if you want, this is like this corresponds to the holomorphic part in some way of this is like the chiral part in some way of the amplitude. So if I define it like this, there is actually an additional coefficient, but I don't want to talk about it. If I define it like this, this is actually nothing more than this W coefficient. This corresponds to the W coefficient at P as a function of nu. And this guy, I can also view it as an operator on the set of functions depending on P and nu. Okay, I can view it as an integral kernel on function of nu and P. So it's really like the Fourier transform of the Liouville amplitude. And I have renormalized so that I don't see the metric anymore. Because of this thing, you can check with the conformal anomaly that this is actually independent of the metric. So now I want to see this block amplitude of sigma 1. Of sigma 1, I put a J1 because it just depends on the complex structure, but not on the metric now. I want to see how this is, if I deform my complex structure, how this B is moving. And this will give me this identity, essentially. So for this, I will make a deformation using this idea of flow of neuromorphic vector field. So what we do, we embed, let's say, this point into the complex plane by adding some disk. So this is nothing more than the sphere. X1, X2, X3. This is sigma. Maybe, okay. This you can also view it as 1 I, where this is a uniformizing map, putting these 3 points on 0, 1, and I. And I will use a vector field, VZDZ, which is going to be a little bit like what Remy said, minus Z plus epsilon Z, or minus epsilon Z to the power n plus 1 dz. This. I consider its flow. I have, okay, maybe I just put 2i here of the unit circle here. And I take its flow, ft. So if I take the image of my 3 curve here, okay, maybe it's not the unit circle, but let's assume. Otherwise, we can always reduce to that case in some way. So maybe this curve is mapping to the unit circle, and maybe this curve here is mapping to a curve here. So it's not always possible to make it the unit circle, but I don't want to pay attention to this. Let's assume this. So my pair point is the outside of this 3 disk now viewed in C, and I want to look at this flow where I deform this curve here, this red curve, by this ft, which is the flow of this vector field. I get a new curve here, the blue curve, and then I use what Remy explained. If I change my point by moving just the red curve to the blue curve at time t, and I differentiate, what you can check to computation, you can check that the derivative at t equals 0 of the block amplitude of sigma t, J is just the complex structure of C, and I put C now dependent T, of mu1, mu2, mu3. Or, yeah, I view it as an operator now on the set of Young diagrams. P. This is actually going to be B composed with the sum of Vn Virasoro component for n in Z. Sorry, I took a name. Maybe I should put n0. So yeah, so here should be, then it should be epsilon ln. So what you, and then you have actually just ln. So what you get is that if you differentiate your block amplitude by this move of just one curve, you're going to compose your block amplitude by the Virasoro component ln actually. On the first entry, what I mean is is you act just on the new one here. So this is something which is a consequence of what Remy explained using this propagator. And the idea is that you just come back to the definition. If you differentiate this guy, the psi is not moving, so you're differentiating the Liouville amplitude here. And this Liouville amplitude when you move by a holomorphic flow, it's a bit like gluing. It's equivalent actually to gluing this little annulus. So you're really moving your amplitude. You differentiate using the formula of Riemann, you actually get this thing. And now to get the full Ward element, so and then this tells you that in general, for if you take V, V1, V2, V3, three local holomorphic or meromorphic vector field near the three curve, these three curve here, this one, and this one. You flow them, you use this principle. What you get is that the derivative of the block amplitude of sigma t, where I move the three curve at the same time with the three vector field associated to each of the curve at t equals 0. What I get something similar. I get BP of LV1 tensor identity plus identity tensor LV2 identity plus identity tensor LV3. And what are these LV? LV is equal to the sum of Vn Ln for n in Z, where V equal sum of Vn Z n plus 1 for n in Z. So if you take your meromorphic vector field, you take its flow, you look at sort of quantization, you actually see that it's like composing the block amplitude by this LV1 on the first component, and LV2 on the second component, and LV3 on the third component. And now the Ward is basically, you do this picture, you do it with V1, V2, V3, which come from a unique vector field. So what you do, you take a meromorphic vector field, which let's say has just one pole at 0, and it's meromorphic everywhere on the plane, including it's holomorphic at infinity, holomorphic here, and holomorphic here. If you use just one flow, the flow of this global meromorphic vector field, it means the V1, V2, V3 are basically the same. It gives you, you're moving your domain by a global flow of biholomorphism. And then you use this idea I was saying, that the amplitude does not move essentially. And it gives you an identity on the block amplitude that I will write, and then I will finish here. And the identity is the following. And this relates somehow to the classical definition of the block by Frankel and other people. So it's another version of Ward, if you want, is that for any V meromorphic vector field on the Riemann sphere with pole at Z equals 0 only, what you get is that you get that the sum for J equal 1, 2, 3 of BP composed with L, V, J, J is 0, where V 1 equals, if you want, V, no, sorry, and V2 equal minus V, and V3 equal minus V. And what is LVJ? J is just J is just identity. Then at the place of J you put LVJ, and then identity on the other. And LVJ is defined this way. So you take the Laurent coefficient of your vector field. Yeah. Yes. And the nice thing is that if you take a meromorphic vector field, this guy has only negative Laurent expansion at 0. But these two guys are actually holomorphic, so they have only positive. And the next, it means that if you take a L minus n in the first component, which come from this pole, you can actually transfer it to some positive ln on the other two poles. And a positive ln, because you act on this guy, which are killed by the positive ln except the L0, it means you can actually compute the matrix coefficient completely intrinsically in terms of this Laurent coefficient of this vector field at these 3 points. That's roughly the idea. So just to say that it's a way to encode, if you want, the deformation by local bihomorphism generated from local vector field. And here I cheated a bit. This is only true if you take circles here, parametrization by circles or Moebius transform. If you do it by a more complicated, if the curve here is not parameterized by Moebius transform, there is actually some Schwarzian term in addition to this, some Schwarzian derivative of this parameterizing map of the curve. And okay, this is all I wanted to say, I think.
Cool. Question?
So this definition here is a statement in a way.
Yes, in some sense. So this is the block amplitude for one point. But if you have a surface, you can glue them now, a little bit like for the Liouville amplitude, you pair them into this Hilbert space. Here, the Hilbert space is just going to be the Hilbert space L2 of the key variable times the Young diagrams, basically, which is the same as the Riemann module, in fact. Yes?
So this bootstrap equation over here, I didn't quite understand why it's a bootstrap equation. Are you suggesting to do the decomposition in different ways on the?
Yes. Well, bootstrap, at least the way I understand bootstrap is just that you write n-point correlation function in terms of 3, so it's sort of bootstrap. And indeed, there is this question of crossing symmetry, for instance. Here it's really based on one decomposition. First, it's one topological decomposition. And there is also this issue with the curves. Turns out that really when you move the curve, this guy is moving a bit. Okay. But now you can ask what happens if you decompose it in two different topological ways also.
Okay, so this is really like half of the bootstrap equation. You do it, you apply it 2 times, and then you get something.
Yeah, you can do it in any way you want. And in principle, you should create a representation of my class group in the space of block, for instance.
Very cool.
So this part is not completely finished, but it should follow from the block construction in principle. Representation. And of course, it gives you some constraint if you do it in 2 different ways. You know probably better than me, but this is used a lot in physics to find, for instance, the 3-point function or certain critical exponent.
Okay, I think we can think Colin again.